Threading is the process of creating a screw thread. More screw threads are produced each year than any other machine element. There are many methods of generating threads, including subtractive methods, deformative or transformative methods, additive methods, or combinations thereof. Overview of methods. There are various methods for generating screw threads. The method chosen for any one application is chosen based on constraints time, money, degree of precision needed, what equipment is already available, what equipment purchases could be justified based on resulting unit price of the threaded part, etc. In general, certain thread-generating processes tend to fall along certain portions of the spectrum from toolroom-made parts to mass-produced parts, although there can be considerable overlap. For example, thread lapping following thread grinding would fall only on the extreme toolroom end of the spectrum, while thread rolling is a large and diverse area of practice that is used for everything from microlathe lead screws to the cheapest deck screws. Threads of metal fasteners are usually created on a thread rolling machine. They may also be cut with a lathe, tap or die. Rolled threads are stronger than cut threads, with increases of 10% to 20% in tensile strength and possibly more in fatigue resistance and wear resistance. Subtractive methods. Thread cutting, as compared to thread forming and rolling, is used when full thread depth is required, when the quantity is small, when the blank is not very accurate, when threading up to a shoulder is required, when threading a tapered thread, or when the material is brittle. Taps and dies. A common method of threading is cutting with taps and dies. Unlike drill bits, hand taps do not automatically remove the chips they create. A hand tap cannot cut its threads in a single rotation because it creates long chips which quickly jam the tap, possibly breaking it. Therefore, in manual thread cutting, normal wrench usage is to cut the threads 1/2 to 2/3 of a turn, then reverse the tap for about 1/6 of a turn until the chips are broken by the back edges of the cutters. It may be necessary to periodically remove the tap from the hole to clear the chips, especially when a blind hole is threaded. For continuous tapping operations, specialized spiral point or gun taps are used to eject the chips and prevent crowding. Single point threading, also colloquially called single pointing, is an operation that uses a single point tool to produce a thread form on a cylinder or cone. The tool moves linearly while the precise rotation of the workpiece determines the lead of the thread. The process can be done to create external or internal threads. In external thread cutting, the piece can either be held in a chuck or mounted between two centers. With internal thread cutting, the piece is held in a chuck. The tool moves across the piece linearly, taking chips off the workpiece with each pass. Usually 5 to 7 light cuts create the correct depth of the thread. The coordination of various machine elements including lead screw, slide rest, and change gears was the technological advance that allowed the invention of the screw cutting lathe, which was the origin of single-point threading as we know it today. Today engine lathes and CNC lathes are the commonly used machines for single-point threading. On CNC machines, the process is quick and easy due to the machine's ability to constantly track the relationship of the tool position and spindle position. CNC software includes CAN cycles, that is, pre-programmed subroutines, that obviate the manual programming of a single-point threading cycle. Parameters are entered, and the machine does the rest. All threading could feasibly be done using a single-point tool, but because of the high speed and thus low unit cost of other methods, single-point threading is usually only used when other factors of the manufacturing process happen to favor it. Thread milling. Threads may be milled with a rotating milling cutter if the correct helical toolpath can be arranged. This was formerly arranged mechanically, and it was suitable for mass production work although uncommon in job shop work. With the widespread dissemination of affordable, fast, precise CNC, it became much more common, and today internal and external threads are often milled even on work where they would formerly have been cut with taps, die heads, or single pointing. Some advantages of thread milling, as compared to single-point cutting or taps and dies, are faster cycle times, less tool breakage, and that a left or right-hand thread can be created with the same tool. Additionally, for large, awkward workpieces, it is simply easier to let the workpiece sit stationary on a table while all needed machining operations are performed on it with rotating tools, as opposed to rigging it up for rotation around the axis of each set of threads. There are various types of thread milling, including several variants of form milling and a combination of drilling and threading with one cutter, called thrilling. Form milling uses either a single or multiple form cutter. In one variant of form milling, the single form cutter is tilted to the helix angle of the thread and then fed radially into the blank. The blank is then slowly rotated as the cutter is precisely moved along the axis of the blank, which cuts the thread into the blank. This can be done in one pass, if the cutter is fed to the full thread depth, or in two passes, with the first not being to the full thread depth. This process is mainly used on threads larger than 1.5 in. It is commonly used to cut large lead or multiple lead threads. A similar variant using a multiple form cutter exists, in which the process completes the thread in one revolution around the blank. The cutter must be longer than the desired thread length. Using a multiple form cutter is faster than using a single form cutter, but it is limited to threads with a helix angle less than 3 degree. It is also limited to blanks of a substantial diameter and no longer than 2 in. Another variant of form milling involves holding the cutter's axis orthogonally and feeding the cutter in a toolpath that will generate the thread. The part is usually a stationary workpiece, such as a boss on a valve body or a hole in a plate or block. This type of thread milling uses essentially the same concept as contouring with an end mill or ball-nose mill, but the cutter and toolpath are arranged specifically to define the contour of a thread. The toolpath is achieved either using helical interpolation or a simulation of it using extremely small increments of 3-axis linear interpolation. The cutter geometry reflects the thread pitch but not its lead. The lead is determined by the toolpath. Tapered threads can be cut either with a tapered multiple form cutter that completes the thread in one revolution using helical interpolation, or with a straight or tapered cutter whose toolpath is one or more revolutions but cannot use helical interpolation and must use CAD/CAM software to generate a contour-like simulation of helical interpolation. The tooling used for thread milling can be solid or indexable. For internal threads, solid cutters are generally limited to holes larger than 6 mm, and indexable internal thread cutting tools are limited to holes larger than 12 mm. The advantage is that when the insert wears out it is easily and more cost-effectively replaced. The disadvantage is the cycle time is generally longer than solid tools. Note that solid multiple form thread cutting tools look similar to taps, but they differ in that the cutting tool does not have a back taper and there is not a lead and chamfer. This lack of a lead and chamfer allows the threads to be formed within one pitch length of the bottom of a blind hole. Thrilling is the process of threading and drilling internal threads using a specialized cutting tool on a CNC mill. The cutting tool tip is shaped like a drill or center cutting end mill, while the body has a thread-shaped form with a countersink cutter form near the shank. The cutter first plunges to drill a hole. Then the thread is circularly interpolated just like the multiple form cutter described above. This tool drills, chamfers, and threads a hole all in one compact cycle. The advantage is this process eliminates a tool holder, and tool change. The disadvantage is that the process is limited to hole depth no greater than 3 times the diameter of the tool. Thread grinding is done on a grinding machine using specially dressed grinding wheels matching the shape of the threads. The process is usually used to produce accurate threads or threads in hard materials. A common application is ball screw mechanisms. There are 3 types: center-type grinding with axial feed, center-type and-feed thread grinding and centerless thread grinding. Center-type grinding with an axial feed is the most common of the 3. It is similar to cutting a thread on a lathe with a single-point cutting tool, except the cutting tool is replaced with a grinding wheel. Usually a single ribbed wheel is used, although multiple ribbed wheels are also available. To complete the thread, multiple passes are commonly required. Center-type and feed thread grinding use a grinding wheel with multiple ribs that is longer than the length of the desired thread. First, the grinding wheel is fed into the blank to the full thread depth. then the blank is slowly rotated through approximately 1.5 turns while axially advancing through 1 pitch per revolution. Finally, the centerless thread grinding process is used to make headless set screws in a similar method as centerless grinding. The blanks are hopper-fed to the grinding wheels, where the thread is fully formed. Common centerless thread grinding production rates are 60 to 70 pieces per minute for a 0.5 in long set screw. Thread lapping, rarely, thread cutting or grinding will be followed by thread lapping in order to achieve the highest precision and surface finish achievable. This is a tool-room practice when the highest precision is required, rarely employed except for the lead screws or ball screws of high-end machine tools. Threading with EDM, internal threads can be electrical discharge machined into hard materials using a sinker-style machine. Deformative or transformative methods, thread forming and rolling. Thread forming and thread rolling are processes for forming screw threads, with the former referring to creating internal threads and the latter external threads. In both of these processes threads are formed into a blank by pressing a shape tool, commonly called a thread rolling die against the blank, in a process similar to knurling. These processes are used for large production runs because typical production rates are around 1 piece per second. Forming and rolling produce no swarf unless material is required because the blank size starts smaller than a blank required for cutting threads. There is typically a 15 to 20% material savings in the blank, by weight. A rolled thread can often be easily recognized because the thread has a larger diameter than the blank rod from which it has been made. However, necks and undercuts can be cut or rolled onto blanks with threads that are not rolled. Also, the end of the screw usually looks a bit different from the end of a cut thread screw. Materials are limited to ductile materials because the threads are cold-formed. However, this increases the thread's yield strength, surface finish, hardness, and wear resistance. Also, materials with good deformation characteristics are necessary for rolling. These materials include softer metals and exclude brittle materials, such as cast iron. Tolerances are typically A plus or minus 0.001 in, but tolerances as tight as A plus or minus 0.0006 in are achievable. Surface finishes range from 6 to 32 microinches. There are 4 main types of thread rolling, named after the configuration of the dies: flat dies, 2-die cylindrical, 3-die cylindrical, and planetary dies. The flat die system has 2 flat dies. The bottom one is held stationary and the other slides. The blank is placed on one end of the stationary die and then the moving die slides over the blank, which causes the blank to roll between the 2 dies forming the threads. Before the moving die reaches the end of his stroke, the blank rolls off the stationary die in a finished form. The 2-die cylindrical process is used to produce threads up to 6 in diameter and 20 in length. There are 2 types of 3-die processes. The first has the 3 dies move radially out from the center to let the blank enter the dies and then closes and rotates to roll the threads. This type of process is commonly employed on turret lathes and screw machines. The second type takes the form of a self-opening die head. This type is more common than the former, but is limited by not being able to form the last 1.5 to 2 threads against shoulders. Planetary dies are used to mass-produce threads up to 1 in diameter. Thread forming is performed using a fluteless tap, or roll tap, which closely resembles a cutting tap without the flutes. There are lobes periodically spaced around the tap that actually do the thread forming as the tap is advanced into a properly sized hole. Since the tap does not produce chips, there is no need to periodically back out the tap to clear away chips, which, in a cutting tap, can jam and break the tap. Thus thread forming is particularly suited to tapping blind holes, which are tougher to tap with a cutting tap due to the chip buildup in the hole. Note that the tap drill size differs from that used for a cutting tap and that an accurate hole size is required because a slightly undersized hole can break the tap. Proper lubrication is essential because of the frictional forces involved, therefore a lubricating oil is used instead of cutting oil. When considering the blank diameter tolerance, a change in blank diameter will affect the major diameter by an approximate ratio of 3 to 1. Production rates are usually 3 to 5 times faster than thread cutting. Thread casting and molding. In casting and molding, the threads are directly formed by the geometry of the mold cavity in the mold or die. When the material freezes in the mold, it retains the shape after the mold is removed. The material is heated to a liquid, or mixed with a liquid that will either dry or cure. Alternately, the material may be forced into a mold as a powder and compressed into a solid, as with graphite. Although the first thoughts that come to mind for most machinists regarding threading are of thread-cutting processes, Smid points out that, when plastic bottles for food, beverages, personal care products, and other consumer products are considered, it is actually plastic molding that is the principal method of thread generation in manufacturing today. Of course, this fact highlights the importance of the mold makers getting the mold just right. Cast threads in metal parts may be finished by machining, or may be left in the as-cast state. Whether or not to bother with the additional expense of a machining operation depends on the application. For parts where the extra precision and surface finish is not strictly necessary, the machining is foregone in order to achieve a lower cost. With sandcasting parts, this means a rather rough finish. But with molded plastic or die-cast metal, the threads can be very nice indeed straight from the mold or die. A common example of molded plastic threads is on soda bottles. A common example of die-cast threads is on cable glands. Additive methods. Many, perhaps most, threaded parts have potential to be generated via additive manufacturing, of which there are many variants, including fused deposition modeling, selective laser sintering, direct metal laser sintering, selective laser melting, electron beam melting, layered object manufacturing, and stereolithography. For most additive technologies, it has not been long since they emerged from the laboratory end of their historical development, but further commercialization is picking up speed. To date, most additive methods tend to produce a rough surface finish and tend to be restricted in the material properties that they can produce, and thus their earliest commercial victories have been in parts for which those restrictions were acceptable. However, the capabilities are continually growing. Good examples of threaded parts produced with additive manufacturing are found in the dental implant and bone screw fields, where selective laser sintering and selective laser melting have produced threaded titanium implants. Combinations of subtractive, additive, deformative, or transformative methods, often subtractive, additive, deformative, or transformative methods are combined in whatever ways are advantageous. Such multidisciplinary manufacturing falls under classifications including rapid prototyping, desktop manufacturing, direct manufacturing, direct digital manufacturing, digital fabrication, instant manufacturing, or on-demand manufacturing. Inspection. Inspection of the finished screw threads can be achieved in various ways, with the expense of the method tailored to the requirements of the product application. Shop floor inspection of a thread is often as simple as running a nut onto it or a bolt into it. This is plenty good enough for many applications, although it is not good enough for most commercial manufacturing. Higher precision methods are discussed below. Commercial-grade inspection of screw threads can involve most of the same inspection methods and tools used to inspect other manufactured products, such as micrometers, vernier or dial calipers, surface plates and height gauges, gauge blocks, optical comparators, white light scanners, and coordinate measuring machines. Even industrial radiography can be used, for example, to inspect internal thread geometry in the way that an optical comparator can inspect external thread geometry. Conical micrometer anvils, specifically suited to resting on the sides of the thread, are made for various thread angles, with 60 degree being the most common. Mix with such anvils are usually called thread mix, or pitch mix. Users who lack thread mix rely instead on the 3-wire method, which involves placing 3 short pieces of wire of known diameter into the valleys of the thread and then measuring from wire to wire with standard anvils. A conversion factor is then multiplied with the measured value to infer a measurement of the thread's pitch diameter. Tables of these conversion factors were established many decades ago for all standard thread sizes, so today a user need only take the measurement and then perform the table lookup. The three-wire method is also used when high precision is needed to inspect a specific diameter, commonly the pitch diameter, or on specialty threads such as multi-start or when the thread angle is not 60 degree. Ball-shaped micrometer anvils can be used in similar fashion. Digital calipers and micrometers can send each measurement as it occurs through an interface to storage and as input to software, in which case the table lookup is done in an automated way, and quality assurance and quality control can be achieved using statistical process control. History: each method of thread generation has its own detailed history. Therefore a comprehensive discussion is beyond the scope of this article. But much historical information is available in related articles, including screw history, screw cutting lathe history, automatic lathe history, screw thread history of standardization, turret lathe, various sections, casting and its family of articles, grinding and its family of articles, additive manufacturing historical development and broadening applications, various specific additive manufacturing articles, list of emerging technologies, cold rolling. The first patent for the cold rolling of screw threads was issued in 1836 to William Keene of Monroe, NY. However, the dies for rolling the threads onto the screw blanks were made of cast iron, which is brittle, so the machine was not successful. The process languished until 1867, when Harvey J. Harwood of Utica, New York filed a patent for the cold rolling of threads on wood screws. Further efforts to cold roll threads on screws followed, but none seemed to meet with much success until Hayward Augustus Harvey of Orange, New Jersey filed his patents of 1880 and 1881. Charles D. Rogers of the American Screw Company of Providence, Rhode Island made further refinements to the process of rolling threads onto screws. References: Bibliography, DeGarmo, E. Paul. Black, J.T. Kuza, Ronald A., Materials and Processes in Manufacturing, Wiley, ISBN A0-471-65653-4. Green, Robert E. A.L., Machinery's Handbook, New York, New York, USA, Industrial Press, ISBN A978-0-8311-2575-2A. Smid, Peter, CNC Programming Handbook, New York, Industrial Press, ISBN A9780831133474, LCCN A207045901. Stevenson, David A. Agapia, John S., Metal Cutting Theory and Practice, Marcel Decker, ISBN A978-0-8247-9579-5. Stevenson, David A. Agapia, John S., Metal Cutting Theory and Practice, CRC Press, ISBN A978-0-8247-5888-2. Todd, Robert H. Allon, Del K. Alting, Leo, Manufacturing Processes Reference Guide, Industrial Press Incorporated, ISBN A0-8311-3049-0. Further reading, Colvin, Fred H., 60 Years with Men and Machines, New York and London, McGraw-Hill, LCCN A47003762A. Available as a reprint from Lindsay Publications. Foreword by Ralph Flanders. Rowe, Joseph Wickham, English and American Tool Builders, New Haven, Connecticut, Yale University Press, LCCN A16011753A. Reprinted by McGraw-Hill, New York and London, 1926. And by Lindsay Publications, Incorporated, Bradley, Illinois. Rowe, Joseph Wickham, James Hartness, A Representative of the Machine Age at its Best, New York, New York, USA, American Society of Mechanical Engineers, LCCN A37016470. OCLCA 3456642, A. Rybczynski, Witold, One Good Turn, A Natural History of the Screwdriver and the Screw, Scribner, ISBN A978-0-684-86729-8. LCCNA 000369888, OCLCA 462,234,518. Various republications are: external links, a video of thread milling with a single form cutting tool,